So centroid sounds like a really cool thing, but it actually just turns out to be the center of mass in the boring case when the density is constant. So there's actually surprisingly little to it. It's just more of a geometric concept than a physical concept, but whatever. So suppose we want to find the centroid of the region where the coordinates satisfy z is non-negative but bounded by 9 minus x squared minus y squared. Okay, so it's always good to know your region. So we sketch this guy out and find out that it looks like a downward opening paraboloid that hits the x y plane here in a disk of radius 3. Okay, so that's our guy. So let's see. So now this looks like a good one for setting up in polar coordinates. If we're going to find the mass, it's going to be, let's see, so we'll set up first the disk across the bottom here, this blue disk. And so that's going to be 0 to 2 pi, 0 to 3. And then z is going to be going from z equals 0, the xy plane, up to 9 minus x squared minus y squared. But like I said, I'm going to do this in polar. So I will call this block right here r squared. And density is constant, so we'll just take it to be equal to 1. And then we are going to be integrating r against dz dr d theta. Okay, and so let's see, so we can pluck out the integral over theta, and that'll evaluate to 2 pi because there's no thetas anywhere else in this business. And then we'll have the integral from 0 to 3 r times, and then integrating the z, we've got 9 minus r squared dr, and then that evaluates to 81 over 2 pi. Now let's look for our moments. So first off, the x moment is going to equal the y moment is going to equal 0 just by symmetry. So you can see that it's this object, as seen from above, is radially symmetric. So the and it's constant density. So the y moment and the x moment are both going to coincide with the origin there. So we can just make a symmetry shortcut. Now notice, if the domain was not symmetric, left, right, or top, bottom, or if the density function were not symmetric, left, right, or top, bottom, then we couldn't make this shortcut. So it's sort of a special thing to do. Now we look for the z moment. So again, setting it up just like we had for the first one. The only thing is that now, since we're looking for the z moment, we're going to throw a z into the integrand with r dz dr d theta. And then we can work this one out. Once again, we'll be able to pull out the theta integral as a 2 pi. And then we have integral from 0 to 3 of, let's see, so that's going to be r times z becomes 9 minus r squared quantity squared over 2 dr. And integrating that out, we get 243 over 2 times pi. So that I used some scratch work to come up with that, but all right. And so now our centroid, x bar, y bar, z bar, is going to be, let's see, so we've got 0 over, and then 81 over 2 pi, and 0 over, again, 81 over 2 pi. And then for our last one, we've got 243 over 2 pi over 81 over 2 pi. So there's our coordinates. And that gives us 0, 0, 3. when you cancel everything off. And so that tells us that the center of mass is like 1/3 of the way up the post, somewhere around here. And maybe that's believable. Okay. One last thing. If you're paying attention, back when I was doing the mass here, I said we have a constant density, so let's just take it equal to 1. Maybe you were wondering, hey, why can you do that? Well, suppose the density was not 1, but it was equal to c. So we've got some number c in here. Well, then I can pull the c out front because it's a constant, and we end up with this c just kind of dangling along. Similarly, when we go to compute the mxy one, we have a c, we can pull the c out in front, and we drag a c along with us wherever we go. Then when we get to the end and we find our coordinate, we've got a c on top and a c on bottom, and guess what? They cancel, so it didn't even matter.